Good day and welcome to this episode of our fluid mechanics, and we are going to be dealing with incompressibility and rotationality of the fluid. I received a message from one of our subscribers that we should do a video on this, so I'll be doing videos on this part today. So we are given this flow. It says show if this flow of an incompressible fluid satisfies the continuity equation. That is, you should check whether this is truly incompressible. No, they've given us this flow and they said they prove it as incompressible. So we have to confirm, and for it to confirm any of this, there's always a continuity equation that you're going to use to confirm. That will be like a proof or determinant for it. So in this case, our continuity equation that we're going to use to check if this is truly incompressible is going to be du dx plus dv dy plus dw dz. So when you add these three entities, it must give us 0. If it doesn't give us 0, that means it is compressible and not incompressible. But if it does give us 0, that means it is truly incompressible. Now let's go on. We are differentiating u with respect to x. We are differentiating v with respect to y, and we are differentiating w with respect to z. So let's move. So your du dx rather. Your du dx. If you differentiate x here, you have minus 1 because you can see it's minus 1 that is here. Then dv dy. Differentiate 2y here. This is the y that we are having. That will be plus 2. So plus 2. Then dw dz. If you differentiate dz, it's going to give you minus 1 here. So let us put the equation together and see whether it is incompressible. So we have minus 1 plus 2 and minus 1. Is this equal to 0? Let's calculate. Minus 1 plus 2 dot minus 1. Yes, it is equal to 0. Minus 1 minus 1, that's minus 2. And minus 2 plus 2 will give us 0. So that means yes, it is incompressible. It is incompressible. We have confirmed it satisfies the continuity equation. This is the continuity equation here. It satisfies this equation, so it is incompressible. So for this one, we said the velocity components in a two-dimensional velocity field for an incompressible fluid are this and this. So we have u with respect to, this is an implicit equation. Also here too, we have implicit equation because it's involving both x and y in the respect to it. So it says you show if this represents a case of an irrotational flow. Now, if you want to check for an irrotational flow, there's a different formula for that. It is different for this one. This one is only for incompressibility, but this one I'm going to write now is for irrotational flow, and that one is dv dx minus du dy. If you look at the equation they gave us, you will see that you can differentiate du dy from here, right? And you can also differentiate the dv dx from here. But you have to be careful because you are dealing with the entity that you are asked to differentiate it with respect to it. So you have to be very, very careful. So let us, this minus this must give us 0. If it doesn't give us 0, that means it is rotational and not irrotational. Do we get? So now let's start. dv dx. Let's start from dv dx. What will our dv dx give us? So we are differentiating x in this place. Now, when you differentiate x here, it will become 1, right? But when you differentiate, you are not differentiating y here because you have to differentiate only x. You are differentiating with respect to x. So whatever y you see there, put it there like that. So what are we having? Since this one is already 1, you have only y squared here. Y squared. So any x again, yes, we have x. We are leaving this one because there is no an entity of x here. So we are leaving it. We are dealing with the one that has x. So when we differentiate x here, what do we have? X raised to power 3. When you differentiate it, that will give you 3x raised to power 2, right? So you have minus 3x raised to power 2 over 3. Automatically this 3 will cancel this 3, right? And we have y minus x raised to power 2. That's for that. And let's come to the u dy. Let's do for the u dy now. So you come here, Now you are differentiating this u with respect to y. Any x that you see beside the y, put it like that and just differentiate only the y. So now let's differentiate y here. You have y raised to power 3. So that means if you differentiate y raised to power 3, you have 3y raised to power 2. So 3y raised to power 2. Remember this, divided by 3 there. Divided by 3. The same thing that happened there too. 3 will cancel 3. It will remain y squared. So let us move on. Do you have any y here? No. So we are leaving this alone. Remember, because we are differentiating with respect to y. So now this has y, it also has x, but we are differentiating with respect to y. So if you differentiate this y, what we have? We have 1. So after that 1, we are not differentiating the x. So you put that x squared there. So x squared multiplied by 1, you still have x squared. So that is minus x squared. So you can see that this and this are having the same result. So now let's insert this into the formula, this continuity equation, whether it satisfies it or not. So you will see that at the end of the day, you have minus y minus x squared on both sides. You see that when you minus this together, it will give you 0 automatically. That means yes, this one is also what? Irrotational. Why? Because it satisfies the equation. When we go to the two entities, when you minus them, you see when you have the y, let's say y is 2 and x also is 2. When you calculate at the end of the day, see that they will give you the same value, and when you minus it from each other, you get 0. That's what makes it irrotational. Thank you very much. This is the end of this video. We are still going to be doing more on this fluid mechanics this season. Help us like. The only way you can help us promote our videos on YouTube is to help us like, share, comment, and subscribe. Share to also those that need it very, very much. Thank you.